All right. So we've gone through our interferometry primer to start off the day. It's always a good way to start off a Sunday, I would think. And so the talk I was going to give now was talking about an instrument I worked on out in Europe called the Prima instrument, which is a new instrument we've put on the VLTI, the Very Large Telescope Interferometer. Basically, the basic notion here is take everything that I told you in this last talk and double it. Why buy one when you can buy two at twice the price? My usual caveat here, which you've already seen. Prima is one of these unwieldy acronyms, like everything is in astronomy. It's phased reference imaging and micro arc-second astrometry. The point behind Prima is to have an interferometer, just like I've talked about, but an interferometer that inside of each telescope you have a field mirror that can split the mirror and give you two different fields simultaneously off of a single telescope. These are separated by about a minute of arc on the sky. And then you have two separate beam lines that go on the back end and combine the light. And what's clever about this is that these beam lines, you monitor the path length in these beam lines with laser metrology. This is actually how you establish whether or not you've hit these very exacting tolerances of tens of nanometers passing through your optical system. And what's clever about this is that if you measure the difference in those path lengths, which is easy because you have laser metrology, that difference translates almost directly into an angle on the sky. The greater this difference, the greater the angle on the sky. And so if you can pull this off, you measure very exactly the angle between two stars. Where it's of interest for us here is that this is very useful for binary stars, for visual binaries on the sky. One of the main motivations that actually I won't talk too much about is the use of this for detection of extrasolar planets. If one of the stars has a planet going around it, the star's position will appear to wobble back and forth over time relative to the other reference star. Interesting little conundrum there is that if you actually detect such a thing, the question is which star is wobbling, but I won't even get into that. That was a cartoon. This is what it actually looks like in practice. The facility down in Chile has four 1.8 meter telescopes move, and I have a video to prove that now. There's also four 8 meter telescopes which also can feed the back end, so it's a very nice facility. It's kind of industrial scale astronomy writ large. In the basement, beneath the facility, you have a crypt-like combining lab where you stuff it full of optics, and this is what the actual Prima table looks like. Interferometry is fun. You actually, rather than having these cans like we saw with Jean Guerre's talk, which are under vacuum, and you can maybe open them up from time to time and tinker with them and then seal them back up, you actually get to walk around inside your instrument. And this is a lot of fun because you get to tinker with stuff. The problem is that then they expect you to walk around inside the instrument, so they send you out to Chile for months on end. And that's kind of trying on family life. There are a lot of subsystems that go into running such a thing. You have telescopes that catch the light. This kind of follows the photon from the outside to the back end. You've got to catch these photons. You have to separate them out between these two stars. You have these delay lines that I showed a picture of in the last slide. You have differential delay lines, so a second set of delay lines to account for the fact that the path difference between your two stars on the sky is slightly different. Normally you could actually do that with one set of delay lines, but it's broken out in a more sensible way for this particular instrument. And you have to track these fringes, these variations in brightness that I showed in the last talk. A number of these things were already in place just to run the interferometer in a single feed mode. That's everything in the blue. And then these red things were all things that were added on top of the existing interferometer to actually get this going. A lot of acronyms. It's definitely an acronym-centric sort of endeavor. This is very hard to get to work. And so this is a cartoon that I used when I was working on the project about how progress went. Unlike John's talk, where the facility was delivered and on sky within a night, by the time I had come and gone with the project over 4 years, we were up to Prima commissioning run 15, I think it was. and it was still a work in progress. So this is difficult stuff to get work. This really is the bleeding edge of astronomy. Early on, we were able to get half of it to work, where you basically turn this thing on, and you can see where the signal noise gets to, I think it's the middle plot here in the purple. When you actually peek up on fringes, you can see the signal noise jump, and then it drops back down when you lose the fringe. The atmosphere over every telescope is pistoning up and down, and you have to track that out. And here you can see the delay line position as it was tracking and following those fringes, and sometimes the atmosphere steals it away from you. So when I was working on this, we early on got it to work. We had some challenges in getting the second channel, the second half of the beam train to work, so we tried some other tricks where we would split the light off of our single beam train and feed it into a mid-infrared instrument that was on the back end as well. What was clever about that is you could actually use this to phase up the instrument, to basically correct the path length along a single beam train in a very precise way, such that if the mid-infrared instrument was tracking itself and trying to account for the fact that the atmosphere is pistoning over each telescope, you get a certain amount of error. And then if you actually correct externally with our fringe tracker at 2 microns, and then just let it look, it locks these things in nice and solid, so the mid-infrared instrument gets a nice clean signal. This is a trick you can use in interferometry to try and clean things up. You sense the light at a separate wavelength to do housekeeping, and then you do the science at a separate wavelength. Within about a year, we were getting to the point of getting multiple beam trains going. So here's a shot showing 2 telescopes, each providing 2 stars. And so 4 stars are what you see, or at least 2 stars doubled. And then trying to get that onto a single fringe tracker. So what that allows you to do is track on 1 star. This is HD 10360 and its companion 10360J. Bad numbering or lettering scheme nomenclature here. And you can see how there's tracks, so there's dropouts in the tracks as these fringes are sensed. A neat trick that you can also do with this is, of relevance here, is look at visual binaries, where you would lock up on a star. I think I have a picture of what it looks like right here. You basically track on a primary star, and then this is many milliarc seconds across, but you can basically scan across this primary star, and you happen to see, actually, in the signal noise of basically if you have a fringe packet or not, you see a big bump for your fringe packet on the primary star, and you see a second little one here because you're actually sensing the position of the second one as well. And so if you zoom in on this, you get very accurate position along one axis of the star. You only get one axis because you have a pair of telescopes that essentially is a ruler on the sky and very high resolution in one axis, but zero position information along the other axis. You can make up for that by letting basically the Earth rotate beneath you again and change the position of the telescopes relative to the star in the sky, or you can have a second pair of telescopes to try and get the orthogonal direction. Ultimately, you want to run everything up at once. This is what it looks like when you're trying to get pairs of stars off of each pair of telescopes, and then you want to track these fringes and see what the signal noise peaks up. I'm trying to remember which trace this is. I think it's this one right here where you were locked on the fringes. And then you try to see if everything works in a rational way, which is difficult. You basically look at the position it tells you on a given night, and then you try it again on the second night, and you see if the answer is the same. Let's see if I can go to the next slide here. This is what it looks like when you're tracking 2 fringes off of 2 stars separately but simultaneously. The position of your primary star is nice and constant. This is in meters, so this is the overall scale here is on the order of microns. And you can see the position of your secondary star, the fringes move around a lot. This is atmospheric piston. This is the relative to your first star, the second star is getting pushed around because you have different clumps of air going over top of the facility. Ultimately, what you want to do is turn this into an astrometric measurement. One trick that this facility does is you feed telescope A and telescope B through one set of optics, and then you actually rotate it and flip it out. And so you can see these measurements going from one particular set of measurements right here, and then you swap back and forth. And that allows you to calibrate out a 0 point in the middle, and then you can look at the difference in path between these particular stars. This measurement, a demonstration of this was done in the late 90s, early noughts with the Palomar instrument that I've worked on as well, back near Palomar Mountain, near the Hale telescope. And so let me show you what sort of potential there is here with this kind of measurement. This is a near and dear binary for us all, 61 Sig. It's a long and storied history for this star. I think it was the first star to have a parallax measurement, culminating in a very interesting competition with Belle and his collaborators many, many years ago. This is a pair of stars. It's a K5 main sequence, K7 main sequence star. They're both very bright. The 2.2 micron magnitude is about 2.5 and about 3 for the other one. And there's a very large orbit. It's at least it's nearby, and it's also slow. It's about 650 years in its period, and it subtends an angle of about 30 arc seconds on the sky. What you can do is you feed this kind of system into this sort of thing I was describing with the Prima instrument, where you feed the primary star down one beam train, the secondary star down another beam train, and you start trying to measure the difference between the two stars in terms of the path length through the interferometer. A single measurement looks like this, where you have a measurement of the primary star. You actually measure the secondary star. You subtract these two, and you get this number at the back end. And this number changes over time, this difference in path length between the two stars, because the Earth is rotating your two stars, and the relative position of the two stars through the system is changing, and that corresponds to a slightly different path length for every observation. Ultimately, that allows you to turn that into astrometry. Another nice thing you want to check is make sure your residuals are Gaussian or quasi-Gaussian. And you can turn this into a position on the sky. So for the Palomar case, here is arc seconds in declination and in right ascension. This is 1990. This is the year 1999, night 185 of the year, and so these are different positions measured, and these are more or less night-to-night positions. You also have to account for the fact that you resolve out the size of the primary star. This is the size of the primary relative to these positions. Mind you, these are individual measurements on individual nights on a 650-year orbit, and you're seeing changes in position on a 650-year orbit. The primary baseline orientation of PTI was north-south, so you're most sensitive to declination changes. But if you zoom in on, say, this 7-night stretch for us, you can see these positions changing over time in declination as you go night to night. You can see the declination. And the residuals are about 100 micro arc seconds. Not milli, but micro arc seconds. This was all motivated by a nice paper done by Mike Shao and Mark Koluvita in '92, talking about how, as you go to longer baselines for interferometry, as you go from, say, a 1-meter aperture to a 10-meter aperture to a 100-meter aperture, you should be able to get to better and better relative astrometric precision. Secondary star between your primary and secondary star, and your error should be getting down to kind of the 100 to 30 micro arc second regime. And this was starting to get into that neighborhood, this measurement we did on 61 Sig. The magic of Prima is that not only are those 1.8 meter telescopes there, once you get it to work with the 1.8 meter telescopes, you can do it with these ever so slightly larger telescopes, these 8-meter mirrors that you have right here with a person for scale. And that should enable some very interesting work, actually. The 1.8s are kind of fun because you can reconfigure them and have them end up at different places on the observing floor up there. And this is the slide I tried to do earlier. These are great. They have onboard generators. You fire them up. It's like, hey, Dad, I'm going to take the car out for a drive, that kind of thing. You get other tricks out of this, too. You can do dual star observing where you phase up the array. You lock the array on a bright star, and then you can go trolling around with the secondary beam to look at fainter things nearby. So what I like about this slide is we actually tried this where we locked on a bright star, and then we used the secondary feed to stare at a second star that was fainter. And normally, when you're trying to zoom through a fringe packet like this, you're trying to beat the atmospheric coherence. It's like like the speckle talks we saw yesterday, where you see each speckle frame go by really, really quick. And the atmospheric coherence time is 2 to 10 milliseconds. You're trying to basically freeze out the atmosphere. When you do it this way, you effectively freeze out the atmosphere in a static way because you're tracking things with your bright star. Each point on this curve is 1 full second in length. We actually totally froze out the atmosphere by looking at this bright star and using it to track the distortions above the site that way. And so we got a nice fringe packet on our secondary star by just dragging the delay line over top of it at that point. You can do some exotic stuff with this. One interesting application of binary stars that you can do is if you look at a fairly widely separated binary, you can look at the separation between those two stars as some massive body like Jupiter goes past one of the nearby stars. So say if you have it pass by one of the two stars, that separation will appear to shift. And the reason for that is a general relativistic effect, basically the bending of space-time. This shows a plot of the celestial sphere and the amount of bending you expect from the major bodies, like the big red spot here is Jupiter. You have maybe Neptune, Uranus, Saturn. And this is the scale. It's on the order of 10 to 50 to 70 micro arc seconds. That sort of thing you should be able to easily measure, actually, with this sort of technique. A trick that I want to do in the future is the ultimate binary star, which is a planet going around a star and actually measure the shadow you see of the planet going in front of the disk of the star. This is more actually of a single star operation than a binary star observation, but it's the sort of thing where if you can image the disk of the star, which we do with these sorts of devices, you can actually image it having a more or less perfect star spot, namely a planet going in front of it. That's basically the thrust of my talk. Are there any questions here?